Welcome, everyone. Thank you for joining us today for the Grasp on Robotics talk series. I'm Lingjie Liu, assistant professor at Penn, and I'm honored to be the faculty host for today's talk. Before introducing our guest today, as a quick reminder, previously recorded talk can be found on our YouTube channel and website. And you will have opportunity to ask questions at the end of the talk. However, if you have questions during the talk, please raise your hand and I can bring you the microphone. Next, it's my great pleasure to introduce our distinguished guest today, Jie Tan. Jie is a senior staff with the scientist and the tech lead manager in the robotics team of Google DeepMind. His research focused on building foundation models and deep reinforcement learning methods to robots, with interest spanning local motion, navigation, manipulation, simulation, and sim-to-wheel transfer. Jie has a lot of famous work. For example, his early work, sim-to-wheel, his recent work, open and Yumi on Lex. Jie is also an adjunct associate professor at Georgia Tech. He got his PhD at the computer graphics lab in Georgia Tech, advised by Greg Turk and Karen Liu. Jie, welcome, and it's a great pleasure to have you, and we look forward to your talk.
Thank you. Yeah. Good morning, everyone. It's a great pleasure to be here today. And I'm Jie, and I'm a director of the robotics team at Google DeepMind. I joined the team about 10 years ago, so almost since the founding of the team. And I have seen a lot of up and downs of the team in the last decade, and also see the paradigm shifts in this area. So today I'm going to share with you some of my experience and observations of this field in the last decade, and talk to you about the remaining challenges towards the AGI in the physical world. Very quick introduction of our team. Our team has 150 people. We are very passionate, hardworking researchers and engineers, and our mission is to solve AGI in the physical world, transforming physical labor with intelligent robots in every domain. You might be wondering, so what does AGI in the physical world mean? So here's my definition. If we achieve AGI in the physical world, you can instruct a robot to complete any task in any environment with human-like quality. So there are three keywords here. The first one is instruct. Right? So you no longer need to program your robot with, with Python, with C++. You should be able to interact and teach a robot using multimodal instructions. These could be natural language. These could be gestures like pointing. These could be your demonstrations. The second keyword is any. It means the robot should be able to generalize to any task and new environments. And finally, human-like. It means that robot should not be robot-like or very slow. Right? It should be agile. You should be able to perform dexterous tasks in a safe manner. So basically, this gives you the 5 key characteristics of AGI in the physical world. They are general, dexterous, agile, interactive, and finally, teachable. Remember that it's very hard to train a robot for all the environment it can encounter in the real world, right? So sometimes it will fail, but it's very important for the human can teach a robot in an intuitive manner. So teachable is a very important part of it. So in the last decade, our team has been pushing really hard towards the frontier of AGI in the physical world. So we have published numerous papers, but today I'm going to just select a handful to maybe review together with you how this work, representative work, has moved the needle. Our team was established like 2015. So soon after that, we build the arm farm. So it's an array of 7 robot arms that is continuously collecting data, and then we use deep reinforcement learning to learn manipulation skills from these data. 2 years later, we start to work in the locomotion area, and we apply deep reinforcement learning in simulation for quadruped locomotion, and we overcome a lot of the sim-to-real gaps so that these policy learning simulation can also work in the real world. 2 years later, we start to use the trajectories from the motion capture of real dogs as the reward function, at least one of the reward function to train these robot dogs. Since then, the robot dogs can move in a very natural locomotion gaits. And this also laid a very solid foundation for a lot of impressive YouTube videos you see. For example, unitary bipedal robots can do dancing or boxing or kung fu, all kinds of amazing human-like motions. And they are all using a very similar technique as this one. It's called deep mimic. So in the last 5 years, we have a sort of switch gear, move slightly away from reinforcement learning towards imitation learning and the robot foundation models. In 2022, we developed RT1, Robot Transformer 1. Basically, the key lesson there is that the transformer architecture is like a data sponge. It can absorb a lot of data. The more data you throw at it, so it's an early sign of life of scaling law for robotics. And in 2022, the same year, we start to realize the power of this neighboring field called large language models. It used to be that the robots don't really understand anything, right? So if you say, make me a coffee, the robot don't know what is a coffee, how to make a coffee. But by embed a large language model into robots, it can start to decompose these long horizon complex tasks into smaller primitive and make a plan and then execute those plans. It basically gives the robot the common sense and world understanding. And in the next year, we double down in this area. So we not only just lean on language models, but this time multimodal language model or vision language models. So it adds a new modality of vision into the system. It learned from the entire internet of videos, text, and so on. So it has much better world understanding. If you build an action on top of that, it carries the generalization to the robot actions. For example, in that time, one of the impressive demo I remember is that you can talk to the robot, say, pick up the toy that represents a extinct animal. Then it pick up the dinosaurs among a clutter of toys. So it really understands these semantics. But we also know that robot foundation model needs a lot of data. In 2023, we have collaborated with more than 20 research institutes to gather data across the globe. And we have open sourced that data set called RTX. And it's probably one of the most used data set that the entire community has trained a lot of robot models using it. And in this year, we start to build on top of the shoulder of the giant, the Gemini model. And we have released 2 versions. In March, Gemini Robotics, and actually 2 months ago, September, Gemini Robotics 1.5. And I'm going to talk about more details in these 2 projects in later part of today's talk. So if you zoom out, you will see that there are 2 distinct phases of our research. In the first 5 years, we worked a lot on reinforcement learning. And in the recent 5 years, we worked on robot foundation models. And this happened to overlap with the 2 paradigm shifts that I observed in robot learning areas. The first paradigm shift is reinforcement learning and sim-to-real solved locomotion. At least people claim so. Just as a reminder where we were 10 years ago. So I don't know how many of you have seen this video. It's a compilation of all the failure examples of DARPA Robotic Challenge. And all these humanoids are tasked to do search and rescue missions. And in this video, you will see that basically one thing, robot falling. They fall, and they fall. So I pause here, but you get my point. But in this year, if you spend $6,000, you can buy a humanoid robot like this. So it can do cartwheel, it can backflip, front flip. It's super agile. It can handstand, balance. It walk naturally, can do motions very similar to humans, similar smoothness and so on. And it can walk and run on different type of terrains very agilely. Okay, let me stop here. So what has happened in the last 10 years? Every time a paradigm shift happens, we should always ask ourselves, what are the underlying driving force that make this happen? So from my perspective, there are three things has happened. The first one is there's a powerful reinforcement learning algorithms that come into existence. I feel very fortunate to join Google in 2015 because it's basically the time that AlphaGo get published, and everyone is so excited about deep reinforcement learning. We have this big hammer, and we are looking for nails. And I happen to be the one working on quadruped locomotion. So PPO just came to existence, I think, a year later, and then we used PPO in pi bullet simulation and trained this quadruped to run. By the way, this is the Minotaur robot. I think it's also from UPenn. It works really well, but you know that if you deploy something, work. This is called sim to real gap. And we have done proper system identification. And the key lesson we learned there is two things very important. You need to get it right. One is the actuator model. So usually simulations don't model them very well. And second thing is latency. Once you get these two things right, your simulation is much closer to your real world. But that's not enough, right? You also need a very robust policy. So we do proper domain randomization as well to improve the robustness of the policy. And after that, you can basically do very challenging galloping motion in the real world. So this is sort of the trigger or starting point of the entire deep reinforcement learning era of locomotion. But even at that time, I'm not a strong believer of deep reinforcement learning. Why? Because it's super slow. I do an experiment. It takes a few days to get the result back. You often need to run like billions of steps in simulation, and it takes a few days. So the research iteration is super slow. Until 3 years later, a group of researchers from ETH and NVIDIA, they developed Isaac Gym. It's probably still widely used today. And it's basically a simulator in runs on GPUs. And you can run thousands of these simulations in parallel. That significantly increase the iteration speed. So basically, you can do reward shaping, curriculum design, all these kind of things for reinforcement learning, and you get results back not in a few days, but in 20 minutes. These two are not enough. If you only have these two, you are doing computer graphics, which was my background. You need a robot. In the same time, this Chinese company called Unitree, they are selling the affordable, capable, and reliable hardware across the globe. And also, they sell to the North America market. A lot of labs actually start to use these robots. So it cost us $50,000 in 2018 for quadruped robots. It sounds very expensive from today's perspective. But at that time, it's actually an order of magnitude cheaper than the alternatives. And as I mentioned that, you can buy $6,000, then you get a very capable humanoid robot. Basically, these three things close a loop. And you have all your ingredients to do reinforcement research in simulation and deploy in the real world. Since you get all the ingredients, a lot of people jump into this area. Then you have positive reinforce and upward spiral. And just in 5-7 years, locomotion gets solved. So I want to highlight this paper. It's not from our group. It's from Amazon very recently. And it's called Omni Retarget. Similar idea that you retarget motion from human motions. And you can see that this is probably one of the most impressive agile demo I have ever seen on a humanoid. At least I cannot do that. So robot already surpassed the human ability. So if you look at the 5 characteristics I mentioned, that this agility seems to work really well. But how about the rest? This is the second paradigm shift I'm going to talk about, which is multimodal foundation model now start to provide robots with world knowledge, common sense, and bring all the generalization into the physical world. Let's start with Gemini Robotics. So in March this year, we released Gemini Robotics. It's our most advanced vision language action model for robotics built on top of Gemini's world understanding. So here is a high-level overview of this method. So we start with Gemini checkpoint here. Right? Then we use robot data set to fine-tune it, so it becomes a robotics model. It has 3 inputs. The first one is visual input, basically the camera images from the robot. And the second is a language prompt. It specifies the task. So what action should the robot take to place orange into the top drawer, for example. And the third input is optional. These are the additional sensor readings. This could be the past actions, it could be proprio, it could be other kind of like tactile sensor if you have them. And these are like robot and task specific, so you can decide whether you want to include them or not. So these 3 things get into the big model, and it's going to predict the robot control targets. And this could be in end effector space or in the joint space. Usually we just use joint angle as the target. And then this goes through the motor controller, typically a PID controller that's going to track these desired targets. So as I mentioned, that these are 3 very important axes for AGI in the physical world: generality, interactivity, and dexterity. So next, I'm going to show you some examples how we had advancing these 3 axes using Gemini Robotics. The first one is generality. As I mentioned, that it's very unlikely that you are going to train the robot for all the possible situations it's going to encounter in this very complex and ever-changing world. So the robot needs to have some way to generalize 0 shot or few shots to the new tasks. So we have come up with a very comprehensive generalization benchmark that has 3 key axes. The first one is called visual generalization. Basically, we want to evaluate the deterioration of your model when you change the lighting conditions, you change the texture, you change the scene, you change or add the visual distractors. How does that affect to the performance of your robot? The second axis is instruction generalization. Remember here, you basically talk to a robot and specify your instruction in natural language. And you can paraphrase your task. You can use a different language, for example, Mandarin, or you can add typos into your instruction. How does the robot react to those kind of variations? And the third type of generalization is called action generalization, where we move the objects around on the table, give the robot different initial conditions. We replace this bottle with some bottle that robot have never seen before, so that the robot need to adapt its motion or adapt its action to check how it generalizes. So from these 3 axes, you can see that Gemini Robotics is twice as good. Here, the metric is success rate compared to the state of art at that time. And here are some of the qualitative examples.
Help me get organized. Let's start by putting the pen with the other pencils.
Okay, I will move the pen with the other pencils.
So it understands, move the pen to the other pencil, what that means. Right? So it has good spatial understanding. And you also see a wide variety of tasks.
Pick up the basketball and slam dunk it.
Okay, I will pick up the basketball and slam dunk it through the net.
So this is my most impressive demo. The robot has never seen this toy. By the way, the film crew, they bought this toy from Target the day before they filmed this. And we have no idea they are going to do this. And the robot data does not contain anything about basketball and anything about slam dunk. But since the model is inherit from Gemini, which has been trained using internet scale data, of course, it has seen videos of basketball and understand what slam dunk mean, and then it carry all the generalization into actions. So the second axis is interactivity. We should be able to interact with the robots using natural language, and the robot should be able to respond to the change of your language and the change of the environment on the fly rapidly.
Can you put the bananas in the clear container?
And there are 3 containers. You need to identify which is the target, the clear container. And you can start to play this adversarial game with your robot.
Can you put the grapes in the clear container?
And sometimes the robot actually hesitates there. So once it sees very out of distribution scenarios, it will hesitate, but eventually it understands it and start to pick out the grapes. So you might feel that the robot is pretty slow. Yes, it is. But I want to say is Gemini is a very big model, right? When you interact with Gemini through a chatbot, it spits out token by token, and you don't feel it's very slow because it's like a natural language. However, if you use it to control robots, often you need like 50 hertz of control speed. And we have to do a lot of work. For example, distillation to smaller models, such as optimizing the serving infrastructure to achieve these kind of speed. So it actually achieved like 5 hertz end-to-end control rate. Not ideal. We are still working on that. And third axis is dexterity, right? We all have a dexterous hand, 5 fingers. We can do a lot of dexterous. And robot manipulation go beyond pick and place and go to this more dexterous domain. For example, folding the glass.
Nice. Now put them in the case.
Okay, I will put them in the case.
And here you have a humanoid with a dexterous multi-finger hand that uses a pinch grasp to pick up the right piece to play tic-tac-toe with you. And this is most impressive demo for that release. It's doing an origami to fold a box head. And paper is just such a weird material. It has very high resistance in bending, and you have to make creases to make it stay in that shape. And there's millions of ways this can go wrong. And also, the robot learns to use tools to actually making a salad. And this is another interesting example is we are trying to install this timing belt, and the timing belt is very stiff, so almost non-stretchable. So you need to pull it with large force, also have the right steps to put it on. And on the left, there's human trying to do it, of course, first time. And it's an interesting competition between robot and humans. The robot wins this time. Yeah, so you see that we have made a lot of progress in dexterity, interactivity, and generalization in Gemini Robotics. And this field is moving really fast. Every time I think about Gemini Robotics, I thought that was last year. Actually, it's only 7 months ago. And 6 months from that, we released a major upgrade called Gemini Robotics 1.5. And it's our most intelligent model to power physical agent. This enables robots to perceive, to think, to use digital tools, and take action to solve more complex multi-step tasks. So in Gemini Robotics 1.5, there are 2 key AI models that work together to power a new agentic experience. So the first model is called the Gemini Robotics ER 1.5. ER stands for embodied reasoning. So it's a reasoning model. It will take in what it sees and the instruction from the humans. It's going to think, right? So what are the steps I need to do? What kind of information I need to gather in order to accomplish the task? During the thinking process, it might think, oh, maybe I need to access some tools. For example, what's the weather like if I'm packing for the human, right? So it can do like weather checking. It can access your curriculums with your permission. So it uses tools to gather information and then form a plan. Then it communicates this plan with the VOA, the vision language action model, so that the VOA can execute it on the robot. So here's one example of that agentic experience.
Hi, Aloha. Can you use my location and sort the objects into the correct compost, recycling, and trash bins?
To perform the sorting task based on San Francisco waste guidelines, I will use the green bin for compost, the blue bin for recycling, and the black bin for trash.
Here we have on our agentic layers, both control the robot and have access to the internet. To sort the trash, I had to look up the rules and look at the objects on the table, think about where each object should go, matching the rules that I had looked up.
The task is complete.
Good job, thanks.
So since there are two models, let's dive into them one by one. The first one is the embodied reasoning model. And so we define the embodied reasoning task are basically the reasoning task that's super important for embodied AI or robotics. For example, object detection, for example, to do the segmentation or pointing, predict trajectories, what you should do in order to accomplish a task, and more importantly, to estimate the progress and success of a task. This is super important. Basically, that gives you the very general value function that you can use not only just during the task execution, but also during I/O training. So we have benchmarked our ER model with on a set of 15 external benchmarks, specifically designed for embodied reasoning. And you see that the ER model 1.5, which is the last bar, is beat all these competitors. One thing I want to highlight is there is also GPT-5 there, right? It's a much bigger model than the ER model. The ER 1.5 is based on the 2.5 Flash. We choose a smaller model because it's really important for robotics applications to be responsive. So we want small latency. But this smaller model actually beats GPT-5 in embodied reasoning benchmarks. Now let's talk about the VLA, Vision Language Action Model. So it used to be that the Vision Language Action Model maps the observation, which is the images and your instruction, into action directly. So they cannot really think or reason. But in this case, the robot can interleave the thinking traces, which are the text, together with the actions. It will basically think first, then act. It can accomplish multi-step tasks while helping people to understand its plan of the actions. It significantly improved the transparency of human-robot interaction.
Can you help me sort my laundry, please?
Sure, I can help with that.
Put whites in white bins and the darks in the dark bin. Beautiful, okay. And then I can now switch this up on it. Sorry, Apollo. And it knows that I have done that and it will react. So this model is able to think while it acts. And I can actually read its thoughts as it's doing the task here. So I can see right now it wants to put the dark blue plants in the black bin, which it's doing, which is great. So you can see the whole flow of its thoughts here, and it's thinking every time it acts. A few months ago, we could only pick one item and put it in a bin. Now with thinking, we're able to ask the robot to chain a whole series of tasks together, and it's completely end-to-end. The thoughts and the actions are interleaved. I can see it running in person, which is really cool.
So now VLA can not only just take actions, but also think before it takes actions. So the next big breakthrough is Gemini Robotics 1.5 can learn across robots and transfer skills zero shot from one robot to another robot. Maybe one analogy is, suppose I've never learned how to drive, but you learned it. But somehow we can all upload our experience to a central server. We all learn from this pool, and then suddenly I acquire a skill of driving. So that's a magic way to expand the robot data set, because you don't have to experience for this robot embodiment. You can leverage the data experience collected on a different embodiment to acquire skills.
This is usually how we train our robots, is actually someone teleoperates the robot, so they have to physically move the robot. And right now, what he's doing is he's training the robot how to do a task. So traditionally, people will train a single model per robot. In Gemini Robotics 1.5, we're actually using a single model across multiple robots. So here's an example. We're hanging things from that workbench. One of the key things in 1.5 is that now all of our other robots can actually do the same task. This actually works on a completely different robot, which is the Aloha robot. That was very nice. This is a good way to understand the learning across embodiments. Aloha has actually played quite a bit with the wardrobe scene. Apollo here has never seen this scene, and we're going to ask it to do something completely new, which is to open this door right here, which is something it's never done before. A little bit more. Can you ask it to pick up the clothes in it? So this is a great example of a completely new motion that is able to learn with the Aloha robots and not just transfer here. Yeah. In the future, where you might have some robots in a particular application, like in logistics, or another robot in a particular application, like in retail, and they're all actually learning from each other, really accelerating the pace at which we can learn to make truly general-purpose robots.
Robotics today. Okay, yeah. The reason is there's a neighboring field that is moving really fast, which is foundation models. And we can basically ride the wave and keep our progress going. So robotics now can leverage multimodal foundation models such as Gemini, translating all the world knowledge into general physical actions. In the future, Gemini is not going to be only constrained in the virtual world. It can actually come alive, be embedded into a robot embodiment, and help you in your daily tasks. As I said, like repeatedly, it's a very exciting time. I just want to maybe tell you a small story. A year ago, it's like also November in the last year, we are preparing a demo for executives. And at that time, it's a very painful experience because nothing works. We want to have a Christmas theme, right? So we buy a socks and a few gifts, and we want to put things into the socks, and we struggle to even lift that sock. But you see today, just 1 year later, right? There are 3 different robots, can do hundreds of tasks in very high success rate. Today, if executives come to the lab, they don't even tell us they are coming. We just need 20 minutes to spin up the robot, and it will be a very impressive demo. At the same time, you have seen a lot of other publications from the community or the models from the community. Just a few days ago, Physical Intelligence, which is a startup in Silicon Valley, they have released the Pi 0.6. It's a new foundation model that shows you that reinforcement learning can significantly improve the success rate. They have a demo of doing coffee, by the way, the proper coffee, espresso machine, not push a few buttons. And they can do it like 30 hours in a row with extremely high success rate. And also, just maybe a few weeks ago, there is this Silicon Valley startup called 1X. Actually, they are from North Europe. And they say that you can put down $200 deposit today. And in 2026, they are going to deliver the humanoid robot to your house. You can own it with $20,000, not super expensive. And it can do all the daily chores for you. Isn't that amazing? So what's the catch? The catch is a lot of these things are not autonomous. There's a human behind and doing the teleop at your home. So there's still a long way to go. So I want to talk a little bit about the remaining challenges. And this is my personal opinion. You might have more challenges. You feel that is super important as well. As we all know, robot foundation model needs a lot of data, but we don't have internet of robots. So we don't have the internet scale of data that was used to train large language model or vision language models. But even worse, we don't have a data flywheel as autonomous driving. So the reason that Tesla self-driving is so good, because everybody drives a car. It's very useful. And at the same time, you are collecting data for Tesla. But no one today is going to buy a robot and then collect data for us. So how do we solve this data bottleneck? And I have heard constant debate between Should we use real data? Should we use simulation data? You might also have heard of this concept of data pyramid. The idea is that you are going to use very noisy but scalable data source at the bottom, like internet scale data, synthetic data, and so on, to do the pre-training, so the robot gets the prior of physical interactions. Then you are going to use very high quality, less scalable data source, such as teleoperation, to calibrate your policy for a specific robot or specialize in certain domains. So let's go through this layer by layer and see where we are and what are the challenges. The top one is teleoperation. On the left, you can see a teleoperator is moving the Aloha robot to do a laundry task. And basically, through this teleoperation, you get all the sensor measurement you need and actuation robot action labels you need to train a VOA. But it's super expensive, right? You need a robot and you need a human in the loop. It's not very scalable. More importantly, it's not feasible for a lot of tasks. If you want to do dexterous manipulation, like screwing some screws, and you don't have tactile feedback, it's nearly impossible to do it. Or if you want to control a humanoid to do some whole body motions, it's also very tedious to do those. But in the last 2-3 years, a lot of the progress in the field are using robot teleoperation data, because these are data yet. But we're going to hit it very soon. The second layer is what I call sensorized human data. You put sensors on human, but now it's you doing the task, not the robot doing the task. And on the left, you see that the Chen, who is the first author of Yumi, he is collecting data at a home environment, wash dishes. And the problem of these is that it can be easily scalable. That's not a problem. That's a good point. And also, I think generalist AI recently said that they have collected 270 hours of Yumi-like data in a year, which is an order of magnitude more than the traditional teleoperation. The problem is there's an embodiment gap. Not all the robots look like humans. I have bi-arm, dexterous hand, or things like that. And also, the action labels, you don't get it for free. Often, you need tracking algorithms or SLAM to reconstruct these action labels, and then you use those to train the robot. So these action labels could be very noisy. The next one is synthetic data. It's always a good idea to translate a hard physical problems of robotics to a scalable computation problems in simulations. The major problem is one called real-to-sim. How can you construct all these environments in simulation that reflect the diversity of the world? And there's also the opposite problem of sim to real. Once you train this model in the simulation, due to the discrepancy between sim and real, it might not work in the real world. People start to investigate not only the traditional physical simulation, but also world models. Nowadays, most of world models are based on the video generation models, like a VO3 or Genie. These models are still not always generate physically plausible outcome, and sometimes it hallucinates. It will play magic. Also, if it's a video model, it generates videos without action labels. So you are facing similar problems. And finally, we use internet scale data. Right? These data are videos, images, text, and these data might not contain the physical interactions, and it might not contain the action labels. But we can always use these to train all the priors about the world, about common sense. And that's exactly what we were doing. So we use the internet scale data to train the Gemini model. Then we use the other layers to add the action layer on top of the Gemini model. So I feel that the progress along all these layers are really rapidly. And I don't think that the data bottleneck is going to last very long. In the next few years, I think that we are not going to be limited by data. So the second bottleneck is hardware. We all know that robot hardware is becoming more capable and affordable. But there's always debate. What is the right embodiment? Which hardware should I work on? My personal opinion is all these different embodiments is probably going to coexist, but I'm a strong advocate of humanoid. So why that? For two reasons. The first reason is because our goal is AGI in the physical world, and our baseline is human. So we need a similar capable and generalizable platform. So why not to use humanoid and compare them with humans? The second reason is often people will ignore because people think the technical merits of different embodiments. But there's one thing, which is influential people. Many cases in history, something gets really successful because there is one person advocate for it. This time it's Elon Musk saying that humanoid is going to be biggest product. Everyone would want one. If Elon says something in Silicon Valley, often people listen. And then there's a lot of venture capitalists that's going to throw money into this problem. And money attracts talents. And then you have this upward spiral. And maybe the humanoid would be the first one get solved. And this is probably why there are so many humanoids companies in the world now. I went back to China 2 months ago. I heard that there's dozens of humanoid companies come into existence every month. But among the humanoid, what's the most challenging part of it? If you ask Elon, he probably will tell you it's a hand. Right? He will say, this is the reason we have not mass-produced a humanoid this year, even though we thought that we are going to. So why hand is so hard? So first of all, hand is a small size. I have seen a lot of hands that's bigger than human hand. But even if it's just 10 to 20% bigger than the human hand, it's too big because a lot of the tools you design for humans, like scissors or some other tools, it will not be usable for a bigger hand. Same time, the human hand is highly dexterous. You have more than 20 degrees of freedom. And if you want to capture that dexterity, you need to squeeze in 20 actuators or more into this small space. So it's a huge engineering challenge. And on top of that, you need tactile sensing. I used to be not a strong believer of tactile sensing because I worked on the Aloha for a long time. And on Aloha, there's no tactile sensing, and it's just a simple gripper. With direct line of sight, it can do a lot of dexterous tasks already. Right? So for example, you can insert a credit card into your wallet. But recently, I started to play with hand, and I have tried to teleoperate the Sharpa hand, which is one of the best on the market. And I've started to realize to control a 5-finger hand without tactile sensing is a disaster. You don't know even what you are doing with a 5-finger hand. And tactile sensing technology has been advanced quickly, but we have not seen on the market something very sensitive, high resolution, but more importantly, durable. So still some time to go before we have a capable hardware. And last but not least, robot safety is critical to real-world deployment. So this was a video leaked from one of the Chinese labs where the unitary human robot started to go crazy and try to hit the researchers around it. Just imagine how scary this could be if the robot is deployed at your home. Yeah, so the robot safety problem is a long tail problem. It's a very long, fat tail, because there's countless out-of-distribution scenarios in home and office environment. At the same time, these robots are in close proximity with humans in these environments. And today, we're using a lot of AI technologies, deep neural networks, billions of parameters to control the robots, and we don't have a full understanding of the underlying technology. Also, robotics is still a nascent field, AI robotics especially, and the safety standards and the policy still falls behind. So these are the 3 challenges, at least on top of my list, that we should tackle. With the challenges and with the amazing progress, I would love to make some predictions like everybody else. So extrapolating forward, what will it look like? So this is a plot of technology readiness over time. And this dashed line is basically when a technology is ready for AGI in the physical world. At that time, you should see robots start to become available. It's everywhere in our environment, in our daily lives. And that's a typical exponential curve. We are all very optimistic. Technology grows exponentially. And the RFM today is a robot foundation model we are all working today. And a couple of years back that we work a lot in reinforcement learning. And I believe we are going to work more on the reinforcement learning going forward as well. And as I mentioned, the data bottleneck should not be a bottleneck for a long time. I predict that in the next 2-3 years, we are no longer limited by data. But are we going to really shoot up like that and cross that line in the next 5 years? Many people believe so. This is why I feel that there is a little bit more, a little bit hype or bubble in AI robotics field. If you look at the history, oftentimes what will happen is like this. Once you conquer some of the key bottlenecks, some other things pop up. Then you are back to square one, right? You need more innovations, more paradigm shift to make progress, to jump on a different exponential curve. This could be the hardware limitations I mentioned, or the safety concerns. Once you overcome that, there's another exponential curve. These might be unknowns that I don't even perceive or can predict today. After that, you probably is going to cross that line. And every time these, pivot point happens, people will get very disappointed because they no longer follow their predictions of this exponential curve. And we call them the winter. But once we cross that curve, so we are going to have a new era called superhuman robots. What that mean? I don't know. There's huge societal impact and implications. But when will that happen? People will have very different answer here. I guess the variance is very high. My gut feeling is it will be after 10 years, but not very longer than that. So I'll put 2035 at this point. Maybe 10 years later, I can come back and see where we are at that time. So we still have 10 years. We need to work really hard to make innovations, paradigm shifts. It also gives us another decade to think about the societal impact and implications of superhuman robots era so that we can prepare for it and we can embrace it once it comes. Before I end, I want to make a quick advertisement of hiring at Google DeepMind. You probably all know that we are working on robot foundation models by now. But what it takes to build the best robot foundation models, I believe there are 3 key components. You need a good base model to start with. You need a lot of data, and you need a lot of compute. We have good base models. Hopefully, you are more convinced about this after Gemini 3.0 release, and also Nano Banana 2. And we have collected a lot of data, both in the real world, and also we have a strong team to work in simulation and world models. We also have a lot of computes. So we are one of the companies that not fully rely on NVIDIA, right? So we have our own TPUs, and all the Gemini training are actually on TPUs. More than that, we have a team of passionate and talented researchers and engineers, and we welcome you to join us. Thank you very much.
Thank you so much, Jie, for the inspiring and amazing talk. Now it's for the Q&A session. Any questions?
Thanks, Doctor. Very impressive talk. And first of all, I want to ask you a question on how do you realize the motion transfer. In the 1.5 paper, you mentioned that you are able to transfer the skills from Aloha to Franca. How do you align different visual difference and the action a joint or how do you control the robot in Latin space actually?
Yeah, it's a great question. So basically, there is a key technique we introduced in Gemini Robotics 1.5. It's called motion transfer. For a lot of confidentiality reasons, we don't disclose them on the tech report. And I cannot talk about the detail today as well. But I can tell you that it's not one technique. It's a collection of techniques on the training recipes that make this possible. So I still want to say, even without motion transfer, if you just pull your data sets from different embodiments together, you should already get some boost on cross embodiment, the deployment, the performance. But the motion transfer is really additional boost on top of that because there are some implicit alignment of the action space.
Hello, thank you for your talk. I want to ask you, what would make Gemini Robotics 2.0 versus like 1.6 or something like that? Is it task methods, some kind of success rate?
Yeah, it's a great question. So first of all, the naming convention of this field becomes kind of weird. I actually don't know what is 2.0, or are we going to do 1.6? Or because you see that pi start from pi 0, then pi 0.5, pi 0.6, pi 0.65 maybe next time. So it sounds like if we converge to 1, we reach the age jack. So yeah, I can talk a little bit about the next version that we are working on. May not call it 2.0. I think a few things that are super important, as I have mentioned in my slides, is data is something really important. So I strongly believe that we should not fully rely on the teleoperation data. We should go really beyond that. So we have started to investigate a lot on simulation data. Actually, even before 1.5, we started to use simulation data, and we started to use world model data. So we have VO and Genie, and then you can make it action conditioned, and you can generate a lot of data using these world models. So I think that from the data front, we definitely should be able to scale it up dramatically. The second thing that we are working on heavily is the success rate. So basically, if you look at the Gemini 1.5, it's like a pre-training checkpoint. So it can do a lot of tasks across different embodiments, but it's not good at any of them. I would say for simple pick and place, it's probably 90% success rate, but for more dexterous tasks, it's probably 40 or even lower success rate. It's not usable in any applications. So we want to boost the success rate, not only on one single task, but generally, so we can get general mastery. It's a very long-term research, but hopefully we are going to make enough progress and put them into the next version of the release.
Thank you, Jay, for the really great talk. You mentioned very briefly at one point that a lot of engineering went into getting VLA model end-to-end performance at 5 Hertz. How much of that engineering can you tell us about? It would be really interesting for me to know, for example, to what extent that was kind of robotics specific stuff, what extent it was kind of general inference speedups, etc.
So yeah, great question. I think it's half and half. A lot of these are just improving the serving mechanism. So this is not only pushed by our team, but also the entire Gemini team, because we are using the Gemini serving inference stack. The second thing is really split the model into 2 parts. One part is doing on the cloud kind of inference for large, like reasoning kind of things, and then a part is doing device. So there is a name from the community called System 1, System 2 to mimic this fast thinking, slow thinking of human. So these are the 2 major techniques.
Thank you.
Hi. I see the VLM model have image input. So how can you infer the 3D position from the 2D image?
How can I infer the 3D position from the 2D image, right? So in the embodied reasoning model, a lot of the output is 2D, actually 2D bounding box and so on. Yes, we do have a 3D bounding box as well. It's not as good as a 2D output, so we are still working on it. But if you have a lot of data that contains both the 2D and 3D information, actually we have a lot of data like RGBD image and so on. Once the once the model take in all these data, it gets a common sense to sort of understand the distance.
Thank you for your talk. I had a question in terms of going from very dexterous tasks, right? I guess you assume that your eyes are pretty much like the best sensor to figure out like distances and all those things between objects. And I guess my question is, how are you going about teaching the algorithm to understand where to look within an image and like make sure that it keeps that detail and information going forward, and maybe to the next task, trying to figure out where the most information-rich part of the image is?
Yeah. So this is an active perception problem. It's not fully solved. In the Gemini Robotics so far, especially in the first version, we don't have active perception. So most of these robots has multiple sensors. For example, Aloha has the top-down sensor that covers the entire space. And then there are 2 wrist cameras. And then there is one from this going forward. So we just take all of them together. And hopefully the the neural network learns the attention mechanism, but we do not actively or explicitly teach active perception.
Thank you for such a wonderful talk. I have a two-part question. So a lot of the common sense knowledge in these systems is coming from Gemini, the non-robotics model. And as you said, one might fine tune it or add more data from teleop, etc., to solve the robotics tasks. And the second part of the question, I'll join them in a bit, is that putting together 2D bounding boxes, 3D bounding boxes, different embodiments, different sensor locations, and then letting the transformer somehow cook this soup is a interesting approach. It contrasted to, let's say, more classical computer vision pipeline, which uses foundation models for each of these tasks individually and then combines them. So the question is as follows. Do we expect that fine-tuning Gemini into robotics is viable as opposed to architectural innovations that are genuinely suited for robotics data? Where do you see these two coming together?
Yeah, that's a great question. So I probably simplify the whole process quite a bit in the talk. What actually happened is we are also the Gemini team. So we actually make architectural changes and adding data to vision encoder training and pre-training process as well. So it's very different from we take an open source model, which a lot of startups do because they don't have full control of a foundation model. Then they basically add data to fine tune it. So it have a very different outcome. So I agree with you that this architecture and which stage you should put data in plays a very important role in robot foundation models. We actually don't retrain Gemini. So again, so Gemini basically have different stages. Say this is a pre-training stage, and this is a torso patch stage. This is and so on and so forth, post-training stage, and then basically they also have clear timelines. So we just need to make sure that we can put our data at the right time into that pipeline, so it will get trained automatically by the entire team with a lot of TPUs.
I see. And the second question about the transformer cooking the soup versus you doing it a little bit prep, you still believe in the first one, I suppose?
I still think that you should get a lot of data. A lot of data can be generated by expert models, right? You're saying you get all the data, some data for bounding boxes, some data for actions, and we do put them together. We basically call this co-fine tuning or co-training. We put everything into a soup, and we believe that a lot of connections or data transfer among these soup is going to happen or emerge automatically through the training process.
Thank you for such an amazing talk. And as you said, it's been really inspiring to see the progress that's been made over the last, even single-digit years. But as you also sort of alluded to, while there's been a great deal of progress, there's still sort of a gap between the kinds of things that robots can do today and the kinds of things that somebody would actually pay money for a robot to do, to put them in a factory to do assembly or agriculture. What do you see sort of the real the gaps, the things that we really need robots to start getting better at doing? And what do you think sort of the challenges, whether they be sensor-based or control-based, that we need to address to sort of get it to that point where somebody would say, here's $100,000, I really need this robot?
Yeah, at the end of the day, it's the cost, right? So the cost and benefit, basically. So if you can calculate and say that it's going to bring us profit, then people are going to adopt them. So what's missing for this cost calculation? Robots are still too expensive, robots are too slow, and the success rate is not high enough. So, and I think that the three things I mentioned are going to address most of these. For example, you always need the robot to be safe. Otherwise, the cost is huge if it damages the environment or human. You need a lot of data. So it's not a special domain specialization because we already have automation for that for structured environment. So you need some generalization, and then you need a lot of data. And then you also need the generalization in order to get high success rate. And the other thing I mentioned is the speed. So currently the robot is very slow, you have seen that. So we need a better hardware, better algorithm to improve the speed. So once we have all these three ingredients, and then you probably calculate the ROI, it starts to make sense, then we can start to deploy and have the data flywheel since then.
Hi, thanks for the nice talk. One thing that I noticed that differs amongst a lot of the robotics companies and startups is their timeline for productionizing. So, there are some startups that are trying to put products on the market right now. Google has the good fortune of being Google and has a lot of money to spend on it. So I'm curious how you guys, with ultimate flexibility, think about when you'd want to like take the technology and make products out of it or get value out of like seeing these things implemented in the real world.
Yeah, I think whenever it's ready, right? We are not in a rush. So I often make an analogy for self-driving as well. There are two very clear, leading players in self-driving. One is Waymo, one is Tesla, right? So Waymo starts from scratch. Say I'm aim for the most like L4, L5 self-driving from the very beginning, and they are not worried about selling cars or selling the service. While Tesla is basically selling cars and use that to earn some money, then sell L2 system, L2 plus system, and going forward. So I think both paths make sense. There is no clear winner now, because even though you feel that it's more scalable in the Tesla way, but maybe they are hitting some glass ceilings. I chat with some of the leaders of Tesla self-driving team. They say that it's really hard actually to take away that safety operator or the driver from the driver's seat. So there is a 0 to 1 again if you want to remove that one person. So similarly for robotics, you can start to find a vertical that you want to integrate, earn some money, and maybe start a data flywheel. Or you can look at your long-term goal, say AGI in the physical world. Think from first principle, what do you need, and solve the problem directly.
I guess a quick follow-up, like in your timeline, do you have like a prediction for when like I would be able to buy a robot from Google, even like the most basic form?
I don't know, to be honest. I also should not predict a product timeline for Google.
Thank you.
Thank you for the talk. I wanted to ask a question regarding the data bottleneck. So I think that definitely like the simulation and sim to real would be part of the thing that would overcome it. But I feel like a lot of simulations right now is based on vision. And like also like you can get the states, but I think the key point that lacks in simulation is like the physical interaction and like the physical rules. And it's like a gap that is, I think like you can use like tactile sensors, a lot of tactile sensors for like certain simulations, but it's still, I feel like it's still a limitation that you can't cover all of the physical rules that's like going on at the same time. So I was wondering like if you have any thoughts of how to overcome this or like any kind of methods regarding this.
Yeah. It's kind of interesting to see simulation slightly different from me. I feel that you said simulation is mostly about visual, but to me, simulation is all about, especially traditional physical simulation, is all about interactions, right? So two things collide, then what is the collision force, then to calculate all these and the response and the change of states and so on. So you also mentioned the tactile sensing. Actually, you can get contact force and so on from simulation as well. It's just very noisy and not accurate because the context is very difficult to model. So how to overcome these? I think that we should definitely put more effort to simulation to make it more physical realism. But at the same time, I think the challenge of simulation is often lies in to recreate the world of diversity. For example, if I just want to simulate this auditorium, all these chairs, all these monitors and so on, I need to painstakingly ask artists to build them from scratch and put them together. I think these are the major challenges of how to leverage simulation data. It's just modeling the world is too hard.
Thank you.
Great talk. I found it really interesting when you showed the video of how the skills can be shared between robots. And I was wondering, since so many different robots are using the same skill, do you guys use this data to further train this skill? And if so, what challenges did you guys face when doing that?
So actually, I need a little bit of clarification of the question. So we have multiple robots to train the skills, right? Some of the robots don't have the skill and do not sync the data. So then it develops skills. So what's the question?
You said that you put the skill into like a central data. Well, in the video, it said it put into a central database, and then that.
That's right.
Yes. So I was wondering, like, what challenges did you guys face making sure that the skills are generalizable enough so it can be used across different robots? And if you guys, when collecting this data, since different robots are, performing this action, you're collecting data, how would you guys retrain the policy and still keep it generalizable enough?
Yeah, that's a good question. I think someone asked a similar question about motion transfer. So there are specific techniques I cannot talk about that actually make it much
Oh yeah, I was
easier.
wondering like what kind of challenges did you guys face? Not necessarily the solution.
Yeah, the challenge is that different robot has very different kinematics, right? And they have different end factors and so on. If we just naively pull all these data together, usually it's very hard for the neural network to extract the common part of it. What will happen is for 3 different robots, the neural network has huge capacity. It's going to create 3 islands of each one for different embodiment. Then you still get some reasonable behavior policy, right, from those. But there is no data transfer or positive transfer among these 3 islands. So it's not improving your learning efficiency, and there is no zero-shot skill transfer between robots. So these are the major challenges. But if you add the motion transfer to it, basically build a bridge or move these islands together so they overlap, then the experience from robot will benefit another robot.
Gotcha. Thank you.
Hey, thank you for the talk. I'm curious what you think about task requiring mobility, especially if the robot needs to do some exploration or figure out what the relevant parts of the scene are. Do you think those skills will come naturally out of the kind of direction that your team is going, or will that require fundamental kind of design changes? Curious to hear.
So Gemini Robotics so far has not touched mobility yet. It's all stationary tabletop manipulation. So mobile manipulation or local manipulation is a very hard problem. We are working on it. But before, Gemini Robotics, our team has worked a lot in mobility, including locomotion and also navigation as well. And we do find that we have a paper called the Mobility VOA, and it's basically using Gemini's understanding of the world and the semantics and so on that can significantly improve your navigation, especially for semantic navigation or open vocabulary language navigation.
A very amazing talk, Professor. Actually, in our most recent research, it's called Maestro. We also used Gemini as a backbone VLM to orchestrating different modules to control the robot. I have 2 questions. So first, in our research, we observed that sometimes Gemini has some hallucination during the task. So sometimes it will think the task has already been done, but actually it's still halfway, and it stops to execute more. So I wonder, do you have some specific methods to solve this?
That's a great question because we face the same challenge as well. Progress estimation and the success detection is super hard. So you can try the latest YA model, but still I think that the accuracy of success detection is not super high. So one thing that we observe is a lot of time there's occlusions. For example, if you just look at one single view, and then you are saying that put things into the container, and the arm happened to occlude the container. So then there can be false positive, false negative. So multi-view will help a lot. So actually we have a multi-view version of that. The second thing is a lot of the success detection problem is very hard. Like zip the lunchbox, for example. And whether the lunchbox is zipped versus not zipped or zipped halfway from your camera far away, it's just a few pixels. So it's very hard to do. It's still an ongoing research for us to improve the progress estimation and success detection. But at the same time, you should use multi-view and also think about, could you change your prompt? We also have a few like prompt changes that has significantly improved success detection.
Okay, thank you. And the second question is, in the most recent released Gemini ER 1.5, you have a VLM and a downstream VLA together. We also, in our project, we also had a downstream Python 5 as a downstream VLA. But we find that sometimes what Gemini as a upstream VLM model, what this does cannot be fully understood by or not super adapted by the Python 5 because it's very limited model, very small compared to Gemini. Yeah. It's very small model, and it sometimes needs formatted input, put something into something like some kind of this. But the out of Gemini is more freestyle. So how do you resolve this? Do you co-train them together in Gemini?
So it's a great question because I know that these kind of problems will come up. We have similar experience if we are using the on-device model. By the way, in addition to the Gemini Robotics, there's the Gemini Robotics on-device model. It is more open and it's based on the Polygemma base model. And we do see that if you have a weaker base model and train it, the ability to handle natural language instruction is much weaker. Basically, the instruction generalization, as I've mentioned, is much worse. So then if Gemini, the VLM model, give you open vocabulary instruction, very likely you are not going to follow it. But for the Gemini Robotics 1.5, it's based on Gemini. So it's actually language understanding is much, much better. And we actually have much less problem of following instructions compared to Grodd, the on-device model, and probably the same for the Pi 0.5.
Okay, thank you.
Yeah, one last question. Sorry. Thank you. Pretty lucky. Yeah, I have a question on the success rate. You just mentioned about people have acceptance with a higher success rate, and one day that will come true. But I'm also wondering, what success rate would you think that Gemini Robotics can get to, and what is success rate that people will accept using that in home? Because I'm thinking Gemini maybe 3.0 still make mistakes, and I feel like that mistake is more tolerance than a robot making a mistake. So do you think the foundation model can actually get to a really high success rate and actually can apply to robot that doing daily life stuff and also around us can actually maybe work in the kitchen or something?
Right. So success rate is also a very nuanced topic. So I cannot give you a number and say at home, now it's deployable because failure has all kinds of categories. There are 4 major failure categories I have identified. For example, in auto distribution scenarios, it will just freeze. You don't know what to do, right? And sometimes it has jerky motions. Sometimes it successfully do one task, but that's not the task you ask it to do. Sometimes it do the task, show the right intention, but fail the task. So there's different acceptance from human, which is tolerable, which is not, right? So I think there was a study by other, researchers saying that maybe the one that's less bearable is it doesn't succeed the task. So yeah, so I don't have one answer for you. It will be a very nuanced answer. And at the same time, it's not all about the success rate, because if you do reinforcement learning on a single task, you can push the success rate very high, but you want a general robot at your home. Yeah. So sorry for maybe unsatisfying answer.
Okay, I think there are still a lot of questions from audience, but due to limited time, we have to stop now. And you can ask the speakers offline. And let's thank our speaker for the fantastic talk again. Okay, at last but not least, some announcement. Please stay tuned for our spring 2026 grasp on robotics lineup coming soon. For more information on upcoming events, be sure follow us on social media or check out our website. Thank you again and have a wonderful day.